Right now, sitting a million miles from Earth, a telescope is staring so far back into time that it is looking at light older than almost anything else humanity has ever directly observed, and what it just found has left cosmologists doing something they almost never do in public: openly admitting their own models might be broken. It has photographed galaxies that, according to the standard timeline of how the universe is supposed to work, simply should not have had time to exist yet. It runs on a mirror unfolded from a shape that had to survive a million-mile journey through the cold vacuum of space. And in the last few years, it has quietly delivered one discovery after another that keeps forcing astronomers back to the drawing board. Scientists aren't calling this surprising. Some of them are using the word impossible and then publishing peer-reviewed papers trying to explain why it happened anyway. Here is the part the headlines are not telling you. Stay with me, because by the time this is over, you will never look at a distant galaxy the same way again. Its name is the James Webb Space Telescope, and its story begins with an almost absurdly ambitious engineering bet. Unlike its predecessor, Hubble, which orbits relatively close to Earth and could be repaired by astronauts, Webb was designed to sit nearly a million miles away at a gravitationally stable point in space called the second Lagrange point, permanently shielded from the sun's heat by a tennis court-sized sunshield folded origami style to fit inside a rocket, then unfurled, piece by piece, with absolutely no possibility of a repair mission if anything went wrong. Engineers openly called the deployment sequence 2 weeks of terror because more than 300 individual failure points, any single one of which could have doomed the entire $10 billion mission, all had to work perfectly, automatically, with no human hands anywhere nearby to fix a mistake. That price tag makes Webb the most expensive single science instrument humanity has ever built, the product of roughly 25 years of design, delay, and redesign involving thousands of engineers across 14 countries. Unlike Hubble, which sits close enough to Earth that astronauts flew repair missions to it 5 separate times over its operational life, Webb's distant orbital position was a deliberate, calculated trade-off. It needed to be far enough from Earth's own heat and light to keep its infrared instruments cold enough to function, which also meant accepting, permanently, that repair would never be an option. The sunshield alone consists of 5 separate, kite-shaped layers, each thinner than a human hair, that had to unfold and tension perfectly in the vacuum of space to keep the telescope's instruments cooled to nearly negative 400 degrees Fahrenheit, cold enough that even the faint heat of the telescope's own electronics would otherwise blind its infrared sensors. When Mission Control finally confirmed, in January of 2022, that every single deployment step had succeeded without a single major failure, veteran engineers who had spent decades building spacecraft described it as one of the most nerve-wracking and ultimately most successful engineering sequences ever attempted. Here is where the first twist in the story arrives. Webb wasn't just built to take prettier pictures than Hubble. It was specifically engineered to see in infrared light, because as the universe expands, light from the most distant, earliest galaxies gets stretched, or redshifted, out of the visible spectrum entirely and into infrared, meaning Hubble, brilliant as it is, was essentially colorblind to huge portions of the earliest chapters of cosmic history. This effect, called cosmological redshift, happens because the universe itself has been expanding since the Big Bang, stretching the space that light travels through and, along with it, stretching the light's own wavelength. The most distant, oldest light in the universe has been stretched so dramatically over billions of years of travel that visible light emitted by an ancient galaxy arrives at our telescopes shifted entirely into the infrared, invisible to human eyes, and to instruments built primarily for visible light, which is precisely the blind spot Webb was engineered from the ground up to eliminate. Webb's mirror, made of 18 hexagonal gold-coated segments that had to align to a precision smaller than the width of a human hair, was purpose-built to catch that ancient, stretched-out light, giving humanity, for the first time, a genuine, detailed look at galaxies as they appeared within the first few 100 million years after the Big Bang. Each of those 18 gold-coated mirror segments can be individually adjusted by tiny motors capable of movements smaller than 1/10,000th, the width of a human hair, a level of precision engineers compared to standing in New York and adjusting a coin's position in Los Angeles down to a fraction of an inch. The gold coating itself, a layer so thin it's measured in millionths of an inch, was chosen specifically because gold reflects infrared light far more efficiently than ordinary mirror coatings, turning what looks, in photographs, like an almost decorative choice into a carefully calculated scientific necessity. But here is the part that stops being abstract and starts being personal. Almost immediately after Webb's first deep field images were released, astronomers spotted something that should not have been possible under the standard model of galaxy formation. Several galaxies, formed within roughly 300 to 500 million years after the Big Bang, that were far too big, far too bright, and far too structurally mature for their age. One team's blunt public assessment became something close to a scientific meme almost overnight. These galaxies, they said, simply should not have had time to form. The comment spread far beyond academic circles, specifically because it captured something rare in modern science reporting. A genuinely blunt, almost startled admission from working professional astronomers that their own predictive models had failed a basic test. Follow-up analysis in the months and years since has refined, though not eliminated, the puzzle. Some of the earliest, most extreme mass estimates for these galaxies have been revised downward as better data came in, while others have held up or even strengthened, keeping the core mystery of unexpectedly early, unexpectedly massive galaxies very much alive in the scientific literature. Think about what that actually means. The prevailing model of how galaxies grow, built, and refined over roughly a century of careful observation, effectively predicted a universe that, in its infancy, should have looked messy, small, and chaotic. Webb pointed its mirror at that same infancy and found, in multiple cases, something closer to a fully grown adult standing where a toddler was supposed to be. Now the story gets stranger. It wasn't just one anomaly. As Webb kept observing, the pattern kept repeating. Researchers cataloging thousands of early universe galaxies found that more than 1,000 of them, dating back over 10 billion years, were shaped like elegant, orderly spiral disks, nearly identical in structure to our own Milky Way, appearing roughly 10 times more frequently than existing models predicted was possible during an era when the universe was supposedly still too young, too cramped, and too violent with galactic collisions to allow such delicate structures to survive intact. Spiral disk galaxies like our own Milky Way are, in a sense, the calm, orderly end result of a long, settling process, stars and gas gradually flattening into a rotating disk over billions of years of gravitational interactions smoothing out earlier chaos. Finding over 1,000 of them already fully formed within the universe's first several billion years suggests either that this settling process happens far faster than existing simulations account for, or that the early universe was considerably less violently chaotic than the standard picture assumes, both possibilities carrying significant implications for how confidently astronomers can model galactic history going forward. Here's the twist that almost nobody outside specialist astrophysics circles is talking about. In 2024, one research team using Webb identified 3 especially extreme cases, since nicknamed red monsters, ultramassive, dust-choked galaxies, each nearly as massive as the entire Milky Way, sitting within the first billion years of cosmic history, forming stars at a rate so efficient it directly contradicted the slow, gradual star formation timeline textbooks had assumed for decades. And in a separate, equally strange discovery, astronomers found a massive early galaxy that displayed something almost never seen at that age. It simply refused to rotate, behaving instead like a galaxy many billions of years older and more settled than its true age should allow. Galaxy rotation is normally one of the more reliable clues astronomers use to estimate a galaxy's age and history, since young, actively forming galaxies typically show messy, disordered motion before gradually settling into an organized spin over billions of years, the same way a stirred cup of coffee eventually settles into a smooth, predictable swirl. A large, young galaxy already showing the settled, non-rotating behavior normally reserved for much older systems flips that entire assumption on its head, suggesting either an unusually violent formation history that erased any rotation almost immediately, or, more provocatively, that the standard timeline for how quickly galaxies mature is simply wrong. The red monsters earned their nickname for a simple reason. Their light appeared unusually red, not because they were especially distant, though they are, but because they're wrapped in thick clouds of cosmic dust that should, according to older models, have taken far longer to accumulate than the young universe had available at that point. Finding that much dust, alongside that much stellar mass, this early, was described by the research team as forcing a genuine rethink of exactly how efficiently the first generation of stars and galaxies were able to build themselves out of raw hydrogen and helium. Stop and sit with that for a second. Multiple, completely independent lines of evidence, massive early galaxies, overabundant spiral disks, a giant galaxy that won't spin, are all quietly pointing in the same uncomfortable direction. Something about how quickly structure formed in the young universe does not match the standard cosmological model as cleanly as scientists assumed it would for the better part of a century. Come back to the science, because there is one more thing worth knowing. These discoveries connect directly to one of the deepest unsolved mysteries in physics: dark matter, the invisible scaffolding that current models say makes up roughly 85% of all the matter in the universe, detected only through its gravitational pull on the galaxies and stars we can actually see. Webb's observations of unusually large early universe structures are now feeding directly into ongoing debates about whether dark matter behaves exactly as the standard model predicts in the universe's earliest moments, or whether something about its behavior, its clumping, its interaction with ordinary matter, needs meaningful revision to explain how galaxies could have assembled themselves this efficiently, this early. Nobody has ever directly detected a single particle of dark matter in any laboratory on Earth, despite decades of dedicated experiments buried deep underground specifically to shield sensitive detectors from interference. Everything we know about it comes indirectly, from watching how galaxies rotate faster than visible matter alone could explain, and how light bends around massive, invisible clumps of something scattered throughout the cosmos. Some of the most convincing indirect evidence comes from gravitational lensing, where the light from extremely distant galaxies gets visibly bent and distorted as it passes near massive foreground clusters, an effect far too strong to be explained by the visible matter in those clusters alone, requiring several times more invisible mass than anything telescopes can directly see. Webb itself has produced some of the most detailed gravitational lensing images ever captured, incidentally mapping the distribution of dark matter across entire galaxy clusters as a byproduct of studying the distant, magnified galaxies behind them. Webb's early galaxy anomalies matter enormously to this field because dark matter is supposed to be the gravitational scaffolding that pulls ordinary matter together into galaxies in the first place, meaning if galaxies formed faster and bigger than expected, the scaffolding itself may need to be rebuilt on paper before anyone can trust the blueprint again. And now comes the moment on the calendar, already locked in, whether we like it or not. Webb's science team has scheduled extensive follow-up observations specifically targeting these early, oversized galaxies through the remainder of this year, using deeper, longer exposure times designed to nail down more precise ages, masses, and distances, hoping to determine once and for all whether these objects are genuinely as impossibly early and massive as they first appeared, or whether some of the estimates will shrink once the data gets sharper. Several similar early red dot-shaped objects, initially thought to be ordinary galaxies, have already been partially reclassified as tiny, unexpectedly massive black holes hiding inside dusty halos, a reminder that this entire field is still actively being rewritten in real time. Distinguishing a genuinely massive, mature early galaxy from an overmassive black hole wrapped in a compact, dusty halo requires extremely precise spectroscopy, breaking an object's light down into detailed wavelength patterns that reveal not just distance and age, but the underlying physical processes producing that light in the first place. Webb's spectrographic instruments are specifically designed for exactly this kind of fine-grained analysis, and much of the telescope's observation time over the coming years is dedicated precisely to re-examining earlier, more ambiguous discoveries with sharper tools, essentially going back to double-check its own most surprising early results. These reclassified objects, informally nicknamed little red dots by researchers scanning Webb's deep field images, turned out in several cases to harbor black holes far more massive relative to their host galaxy than anything seen in the nearby present-day universe, raising an entirely separate puzzle. How do you build a black hole that oversized, that quickly, in a universe barely a few 100 million years old, when the standard model of black hole growth generally requires far more time and far more raw material than these early systems appear to have had available to them? One leading explanation under active investigation involves what astronomers call heavy seed black holes. The idea that instead of growing gradually from the collapse of individual dying stars, some of the earliest black holes may have formed directly from the sudden, dramatic collapse of massive, pristine gas clouds in the infant universe, skipping several intermediate growth stages entirely and starting out already thousands of times more massive than a typical stellar remnant. If confirmed, this would mean the early universe had at least two genuinely different pathways for building black holes, rather than the single, more gradual mechanism long assumed to explain everything we see today. There is something almost unbearably poetic in that. A machine built to answer relatively modest, well-defined questions about how galaxies evolve has instead handed an entire generation of cosmologists a genuine, open mystery. Either our fundamental model of how the early universe assembled itself needs real revision, or these individual objects are stranger and more efficient at building themselves than anyone currently has a clean explanation for. Either answer means the textbooks currently being taught in university classrooms right now are, in some meaningful way, already out of date. This is, in a strange way, exactly what good science is supposed to look like, even when it's uncomfortable. Textbooks in astrophysics have been quietly rewritten before, sometimes gradually, sometimes abruptly, whenever a new instrument finally became powerful enough to test assumptions that had gone unchallenged simply because nobody had the tools to check them. Webb's early universe anomalies may ultimately be remembered less as a single dramatic discovery and more is the moment an entire generation of astronomers had to publicly admit that a century of careful theoretical work, built without any way to directly observe the universe's first billion years, had inevitably gotten some important details wrong, simply because there was no way to have gotten them. Right without a telescope exactly like this one. There are still two genuine open questions science has never fully resolved about this discovery, and neither has an easy answer. The first, are these early massive galaxies genuinely as old and as big as current measurements suggest? Or will more precise follow-up data eventually reveal that some of them are closer, smaller, or younger than first estimated, quietly resolving part of the mystery through better measurement rather than new physics? The second question is more fundamental. If the anomaly holds up under further scrutiny, does it mean dark matter behaves differently in the early universe than our models assume? Or does it point to some entirely different, currently unknown mechanism accelerating how quickly stars and galaxies can form? That window, the unusually clear, uncontaminated view Webb currently has into the universe's first billion years, is a genuinely limited scientific resource, dependent on a telescope with a finite fuel supply for the small thruster corrections that keep it in its precise orbital position. A supply engineers currently estimate could last 20 years or more, but which nonetheless represents a hard, physical limit on how long this particular window into the deep past will remain open. Webb's original design lifetime was a comparatively modest 5 to 10 years, but its flawless launch and deployment meant it consumed almost none of its onboard fuel, correcting early trajectory errors, leaving it with a far larger reserve than engineers had budgeted for. That unexpected fuel surplus, now projected to potentially last 20 years or more, has effectively doubled the telescope's useful scientific lifetime, meaning an entire additional decade of observations into the deep past, and potentially an entire additional decade of anomalies just like these may still be waiting to be discovered. So the next time you look up at the night sky, remember this: somewhere in that darkness, light left galaxies more than 13 billion years ago, before our sun, before our galaxy as we recognize it, before nearly everything you consider familiar in this universe had come into existence, and a machine sitting a million miles from where you're standing is currently the only instrument on Earth capable of catching that ancient light clearly enough to notice something, is genuinely, mathematically strange about it. It was never supposed to break the textbooks this quickly. It just kept looking. And the universe kept answering back with things nobody expected. If this story pulled you into the dark with it, subscribe right now, drop a comment telling me whether you think dark matter itself needs rewriting, and share this with someone who still looks up and wonders what else is hiding in that ancient light. Because Webb's biggest discovery may not be a single galaxy at all, but the growing realization that we understood the early universe far less than we thought.